All right, guys, STAT1800, one-way ANOVA. This is some of my favorite stuff to teach. I love this procedure because there's a lot going on. By the time we learn how to really do one-way ANOVAs, there's going to be actually 3 tests of inference that we have to conduct. So again, a lot going on. By the time you finish this video, your head will be spinning. But my purpose in this video is not to make your head spin, but to just give you a solid foundation on the terminology and the process, the procedure of the one-way ANOVA technique. So guys, the objective here, essentially in this video, I want to teach you how to conduct an ANOVA. Now, last sentence there, well, there's one sentence, but the last line says comparing the difference between the means of more than 2 populations. So if we have a quantitative measurement and we have this divided into 2 populations, then we use a 2-sample t-test. But if we have a quantitative measurement and we divide it into 3, 4, 5, 6, more than 2 populations, then we conduct an ANOVA, which is what I intend to teach you, if you'll let me. The general ANOVA setting, again, the investigator controls 1 or more factors of interest. Let's just say we're talking about, I'll tell you what, let's bring a political example into it because I just think politics has gotten absolutely absurd. But people just lose their minds over it. So, let's say we wanted to look at somebody makes a claim that the IQ is higher for one political party or the other, and trust me, I have friends who are convinced of that. Both sides. I have Republican friends who are convinced that IQs of Republicans has got to be higher than IQs of Democrats, which makes me laugh. And I will equally laugh at the other side where Democrats think that their IQs are higher than Republicans. I seriously doubt there's much difference. In fact, I know there's no difference. There's actually been studies done on that. But anyway, let's get back to the point. If I want to look at the average IQ across Democrats and Republicans, then I'm going to conduct a 2-sample t-test. But what if I want to do average IQ across Democrats, Republicans, and others? Say we get into moderates and independents and all those different things that we have created. Then we would have 3 groups, Democrat, Republican, and others. So we would have to conduct an ANOVA. So guys, that's essentially what we're doing here. Comparing the means of a quantitative variable across 3 or more groups. Completely randomized design, the experimental unit, which is our subjects, are randomly assigned to groups. The subjects are assumed homogeneous, belonging to one group. So there's only one factor independent variable with 2 or more levels. And again, this is a classic ANOVA design. Now, kind of clearly a relative example. Let's examine the difference in average accidents across the 1st, 2nd, and 3rd shift, or the expected mileage for tires across 5 different brands. So again, the assumptions here: the populations are normally distributed, the populations must have equal variances, and the samples are randomly and independently drawn. The hypothesis for a one-way ANOVA, the H sub O, is that mu sub 1 equal mu sub 2 equal mu sub 3, however many groups we have. So we assume that all the population means are equal. And the alternative hypothesis is not all the means are equal. So at least one population mean is different than the other. Now, in the example of looking at the average accidents across the 3 shifts, our null hypothesis would be mu for the 1st shift equals mu for the 2nd shift equals mu for the 3rd shift. And then our alternative hypothesis would just be not all the means are equal. Now, what does that mean? Does it mean they're all different? No, it doesn't. Maybe the accidents for shift 1 and shift 2 are the same, but maybe shift 3 differs from both of them. Or it could be that all 3 are different. So all the alternative says is that there's at least one population mean that differs. Now, we get into something called a Tukey-HSD post hoc. So if we do get significance, if we do reject the null hypothesis, then we conduct kind of a controlled t-test. I'll talk a lot more about that later, to where we can examine which of the means actually are different. Guys, the one-way ANOVA, again, the null and alternative provided there. So when the null hypothesis is true, it means all the means are the same, so there's no factor effect. So we have mu1 equal mu2 equal mu3, so you can see that our distributions are the same. They have the same mean. In the more exciting case, I guess, where the null is not true, it means that at least one of the means are different. The bottom left, you can see where mu1 and mu2 are equal, but mu3 is different than those two. Or to the bottom right, you can see where we could essentially have all of the means different. And guys, in thinking this, I think it's better to think about it less abstractly and think about it more in terms of an example. So, think about this in the context of the number of accidents per shift. Okay. Now, partitioning the variation. This is where ANOVA gets a little strange, a little challenging, I guess. We talk about, okay, let's think about ANOVA, analysis of variance. And I remember many, many, many years ago when I first started taking my statistics sequence, I thought analysis of variance would be analyzing variance to take a look at the variation between groups. Well, it does, but the end goal is to use this variation to examine the differences in means. Now, I think this is one of the most brilliant statistical techniques. It was developed by Fisher, who's one of the greatest statisticians ever. In fact, there's a distribution that we use here. We don't use the t distribution or the z distribution as we've used before. We use the f distribution, which obviously was named after Fisher. So anyway, guys, we have this total variation that we can talk about. And this variation can be split into two parts. Now, the sole reason I'm doing this this first video using a PowerPoint is I love the illustrations that they've created through these PowerPoints. It's the sole reason. All this other stuff I could have spoke through and written it out on notes using the overhead projector. Of course, you couldn't have read most of it, but the whole reason are the pictures. So we'll get to that in just a second. So the total sum of squares just happens to be that we take the overall mean. We take all the measurements, regardless what group they're in, and we just take the overall mean of that. And then we want to look at how far away from the grand mean, as we call it, each of the individual measurements fall. So that's called the total variation. Now that breaks down additively into two subparts of variation. One is called the sum of squares among the groups, and the other is called the sum of squares within the groups. Now, I can sit here and explain that to you. I know this process like the back of my hand, but I promise you, when you see the pictures, it's going to make more sense. The diagrams that they created for this PowerPoint, it's going to make a lot more sense. So what I want you to know now is when we start the ANOVA process, we begin by looking at what are called the sum of squares. And the sum of squares the total sum of squares can be partitioned into two parts, which are add up to the total sum of squares. So partitioning the variation, the total variation again, among group variation and within group variation. Again, I'm not going to articulate that. I'm not going to provide a narrative here because I think the picture provides a much better illustration. So guys, more stuff. So the total variation is essentially the variation that is explained by the factor, and then we have what's called just random error variation. Every statistical model has error because we're dealing with a sample to generalize to a larger population. So the total variation is ultimately the variation that we can explain from the model plus the variation that we can't explain, which is called the error. Now, if that kind of goes over your head a little bit, that's understandable. Again, guys, this is a process. This is not something that you're going to, our assignments are due at 11 and you wait till 8 o'clock to start watching videos. You're going to be in big trouble this week. But if you do that, that's totally up to you. Now, the total sum of squares, you get into a double summation there, which usually drives people crazy. But essentially what you do is you find the grand mean, which is that x with the double bar above it, and you take each individual measurement, regardless of which group they're in, and subtract it from the mean, you square that, and then you add all those measurements up. Now, so I love this picture here. So you can see what's happened. We've got group 1, group 2, and group 3. So you see group 1 are the green dots. And so we have 3 measurements from group 1. Group 2, we have 4 measures, and group 3, we have 4 measures. So if I was to add all these measurements up and divide by 11, 4 plus 4 plus 3, I would get my grand mean. Well, the total variation is found by taking each of those measurements, regardless. We don't even care which group they're in. We keep them in a group, so we really don't care when it comes to the calculation. And we see how far away from the grand mean that each of those measures falls. So we take the measurement, subtract the grand mean, square it for the first measurement. The second measurement, we take the measurement minus the grand mean, we square it, and we just add all that stuff up to get the total variation. Now, the among group variation is, instead of focusing on the individual measurements, it focuses on the means of each of the groups. So this will take the sample size of the first group times the mean of the first group minus the grand mean, square it, and then we'll add to it the sample size of the second group times the mean of the second group minus the grand mean. It'll keep doing that for all the groups. I think this illustration right here, you can see that x bar 1 is the mean of the green dots, x bar 2 is the mean of the fuchsia or purple, or whatever, and x bar 3 is the kind of bluish dots. So there would be 3 calculations here. The sample size 1 times x bar 1 minus the grand mean squared, plus sample size 2 times the mean of the second group minus the grand mean squared, and the sample size, which is 4, times the mean of the third group minus the grand mean squared. The within group variation actually goes within each group and examines the difference between the measurements and the mean of that particular measurement. Now you can see over here, you can see that the first calculation is just going to focus on the mean of okay, let me back up. The within group variation doesn't use the grand mean at all. It just focuses on each group and then adds up that information. So the first 3 calculations would be to take each of the green dots, subtract their values from the mean of the green dots, and square it. And then we would focus over on the group 2 and do the same thing for all 4 of those measures. Take each one of those measures from the mean of the group 2, and then we do the same thing for the mean of the group 3. This will make a lot more sense when I get off the PowerPoint in the next video. Well, actually, the next video will be a brief video on the F distribution, but the next video will actually make these calculations by hand. It'll make more sense. So after calculating the sum of squares, we calculate the mean squares, and it turns out that the sum of squares is just, the mean squares is just the sum of squares divided by the degrees of freedom. So the degrees of freedom, the total degrees of freedom are n minus 1. So in the problem for that we've been looking at with the green dots and the blue dots and all that, our sample size was 11, so the degrees of freedom for the total mean squares would be 10. C is the number of groups, so the degrees of freedom for the mean square among would be 2, 3 minus 2. And then the mean square within, the degrees of freedom would be our total sample size, 11, minus the number of groups, which is 3. So we would have 8 degrees of freedom for the mean square within. And this is some of that stuff you just got to tattoo to the brain. You got to put it in your notebooks. You're probably not going to remember all this stuff for your final exam, so that's the reason I don't require students to come in dry. I let them have notes because it's just way too much to remember. And I'm just getting started bombarding your brain with statistics. And we got chi-square, test of independence, the goodness of fit. We got regression, multiple predictors, dummy value. We got so much stuff coming up that it's insane. So it's the reason I required you to. Well, some of you told me you weren't going to keep a notebook, but you said you would, just to get your points. I thought it was kind of cute. One student said, "I'm going to keep a notebook. Now give me my points, but here's my disclaimer. I'm really not." But that's fine. That's up to him or her. All right, but anyway, there's going to be a lot to remember. All right, guys. Ultimately, once we get our sum of squares and mean squares, we create what's called an ANOVA table, which is in this format. And if you need to copy that down, I don't think I would yet. We're gonna kind of wear this out in a few examples coming up. Well, guys, the one-way ANOVA. What's the test statistic? Well, it turns out that the statistic is an F statistic, not a Z-stat, not a T-stat as we've seen in tests before. This is actually an F-stat because it comes from the F distribution. And guys, unlike the T distribution where you have a degree of freedom n-1, the F distribution has 2 degrees of freedom. So down at the bottom you can see we have degrees of freedom 1, which is the number of groups minus 1, and degrees of freedom 2, which is your total sample size minus the number of groups. So more about that later too. So in interpreting a one-way ANOVA, guys, the F distribution is different than the Z and the T in that the F distribution is never a two-tail. The critical value, the critical region, the reject region, is always in the right tail only of the F distribution. So the ratio will always be positive. We're dealing with positive numbers here. No negative test statistics like we get in a Z or T. And I'll teach you how to, it's very easy, I'll teach you how to find your F critical, and I'll teach you how to find your p-value if you're given an F-stat. And that's actually going to be in the next video. I think the video will probably only take about 5 or 6 minutes, so it's going to be one of those that you're going to like. But it's very, very simple if we've made any connection at all about critical values and p-value calculations. So guys, just run through a brief example here. Let's say you run a business, a manufacturing company of golf clubs, and you wonder, is one golf club hitting the golf ball further than the others? So you get an automated driving machine. I've seen one of those. Those are actually really cool. And you hit 5 balls, and you can see club 1. Again, these are all hit with the same automated driving machine. So to take the quality of the golfer out of it, you get consistency there. So club 1 hit it 254 the first time, 263 the second, and so on. Club 2, club 3 measurements you can see. Upon investigation, it appears to me that club 1 is hitting it further. But that's dangerous, guys, to just look at your sample data and look at the measurements or look at the averages. You need to let the process play its way out. So we're going to test at the 0.05 level. Is there a difference in mean distance? So the first thing they'd want to do is they'd want to make some basic calculations. So you could see that they've calculated the mean of the first 5. So the mean for club 1, the mean for club 2, and the mean for club 3, and they've calculated the mean for all 15 measurements. So the mean for all balls hit, or all clubs hit, is 227. The mean for the first club is 249, 226, and 205 for club 2 and club 3. So upon investigation, we can see that club 1 hit it further, but is that enough away from each of the others to be statistically significant? Well, I don't know yet. again, you got to let the process play its way out, because this assessment of mean differences is based on the ratio of these sum of squares, these variations that we talked about earlier, not just a direct comparison of the sample means. So there's some calculations here, guys. This is going to be very overwhelming to you, I think. And I think until I just go through piece by piece, like I'll do in the next example, I don't think that most of you will get where these numbers come from. You may, I don't know. It doesn't hurt to try. But anyway, they've calculated the sum of squares for both sources of variation. They've come up with the mean squares by taking the sum of squares divided by the degrees of freedom, and they came up with the F statistic of 25.275. Now, the F critical is 3.89 with degrees of freedom 2 and 12. Again, I'll show you how to calculate that in the next video. So our F statistic falls in the rejection region. So we reject H sub O at alpha equal 0.05, and we conclude that there is evidence that indicates that at least one of the means is different from the rest. So guys, when you get a significant ANOVA like we got here, then your focus goes to what's called a post hoc test. And a post hoc test, we'll use Tukey-HSD, the Tukey highly significant differences approach. And luckily for us, all this is done by StatCrunch, which is really cool. So guys, some assumptions again. We have randomness and independence. We have normality for each group. And we have homogeneity of variance. Now, homogeneity of variance is just a big old fancy way of saying that the data appears to come from three populations which have the same variance, the same shape. And these can be tested with Levene's test. So this is kind of something you have to do before conducting the ANOVA to make sure that you're satisfying the homogeneity of variance assumption. So again, we start out looking at a Levene's test before we even conduct the ANOVA. So what's Levene all about? It tests the assumption that the variances of the populations are equal. So if we could hit all golf club 1, all golf club 2, and all golf club 3 infinitely many times, these things would have variances. Well, we want these variations, these measurements of the population, to have equal variances. So first thing, our null would be that all the variances are the same, and then the alternative is that we have violated the equal variance assumption. So the Tukey-HSD actually comes in and identifies which population means are different. So we conduct this stuff after we get a significant ANOVA, or we've rejected H sub O. So it compares these differences. So the output is really easy to compare, and we'll get into that at a later time. But I just want you now to know that before we conduct an ANOVA, we do a Levene test of equal variances to make sure that we're satisfying the equal variance assumption. And then if our ANOVA test is statistically significant, in other words, our p-value is less than our alpha, then we get into paired comparisons. All right? So guys, in summary, what have we done? Well, I have discussed how to use hypothesis testing for comparing the difference between means of more than two populations. A little bit of a word of encouragement here. If your head's kind of spinning and you feel like there was a lot to take in, you're right. There is a lot to take in this this whole ANOVA statistical technique. So guys, hang in there. I'll do my best to break it down into simpler terms as much as I can. So take care.